Now, still with Kerberos version 4, while it was good for MIT, as we started adopting it, there were lots of problems, and the Kerberos version 5 had to be developed. So what are the problems with version 4? First of all, everything was non-standard. Names, instances, realms, everything was limited to 40 characters. And non-standard in the sense that the coding that was used was just somebody's, whatever they thought is right, they did it. For example, your name always ended with a 0, null character. And so that itself is a problem. That itself is a problem because people have found out ways to attack by putting a null in the name and things like that. And they were limited to 40 characters, which is not sufficient for many things. So second thing is DES encryption. So they only use DES, and we know that DES is no longer good. So we could not use AES because it was just built into the protocol. Only IPv4, it was built into the protocol. All the addresses were 32-bit long. You could not use any other protocol, such as ISO CLMP. Any guesses what that might mean? So ISO, we already know, is International Standard Organization. CLMP is Connectionless Network Protocol. So ISO also developed all these protocols. Then there were layer 3, layer 4, layer 5. Sorry, layer 3, layer 4, and layer 5 is application layer. And many of them were implemented. Even though we don't use them very often, but they exist. So there is a ISO network layer protocol, connectionless network protocol, which would be a replacement for IP. They never replace IP, but it exists. So now people want to make sure that that is supported. Names should be encoded by ASN1 because ASN1 is designed for encoding names. And that is what is used in all other places for encoding names, such as in certificates. So that way you can use ASN1. If you use ASN1, then you can use any byte ordering. Right now the byte ordering is indicated by, basically in the message. Okay. Then maximum lifetime is 21 hours because 8-bit lifetime in units of 5 minutes. So 5 minutes times 256 is that 21 hours. The time is 8 bits, 1 byte, and each bit indicates 5 minutes. No delegation. A server cannot allow another server on the behalf of the client. So you could not go to a print server which would give it to another print server. So just direct. Inter-realm authentication limited to pairs. So everybody has to have a secret with the TGS, particularly if you have another realm, their TGS has to have a secret with our TGS, and it has to be direct. So we could not trust them and they could not trust somebody else. So A trusts B and B trusts C does not imply A trusts C, which is a good principle that I cannot trust somebody that you trust, but then it becomes less scalable. Then it becomes difficult to cover the whole world there, cover much longer area because then you have to know n squared. So in some cases it might be okay for you to use that, and so that is where that needs to be generalized. Double encryption of the ticket. So remember the tickets are encrypted inside the key. You notice that one here. This ticket is inside this key, KC, and the ticket itself is encrypted stuff. So why do we need to do double encryption? That is just extra work that we don't need to do. PCB does not detect interchange of cipher blocks. Interesting. So basically, while it propagates the errors to all the blocks, but it has some of its own weaknesses that was not discovered when it was designed. No subsession key for long sessions. So we got one KCB, which is the secret between the client and the server. And if that session was very long, suppose you wanted to use, it was not a print server, let's say it was a database server, and you wanted to use it for a day, then you don't want to use that KCB for a day. You really want to break it down into hours or minutes or something like that. So that was not allowed. and brute force password attack. And there was some way to attack the password. And so anyway, so these 11 things, I have double numbering here, but basically I should have deleted these other numbers. But 11 issues, they were fixed in version 5. So now the names, instance and realms have ASN1 names. They can be of any length. Any encryption scheme can be used. So now encryption scheme is coded. So you'd say that I'm using AES. Any type of addresses can be used. The address type is specified. Byte ordering is ASN1. The explicit start and the end time, so there is no business of 1 byte with 5 minutes. So you can have any lifetimes. Delegation is possible by requesting proxyable tickets. So you could say, I want this ticket that can be assigned from one server to the next. It's a weaker ticket, but you get that ticket, proxyable ticket. So that proxy can use this for you. Inter-realm authentication hierarchy, and that A trust B, B trust C is allowed. So A trust C. No double encryption of the ticket. So ticket is kept separate outside of the encryption. Explicit integrity mechanism detects block interchange, so that PCBC was fixed. Sub-session keys for long sessions, so you could get keys for shorter time. And password attack is made difficult by a pre-authentication mechanism. So all of these problems are fixed. Yeah. Let me see your question. So authentication server, you're saying different realms? Yeah, right. The authentication server in real different realms have to have a secret with somebody. And so let's say if Vashu already has somehow secret with the rest of the world, then if a new realm comes in, all they have to do is just have a secret with Vashu. So then A trust B and B trust C, you can authenticate that way. You don't have to have A and C directly share the secret. You have to remove it, yeah. So the thing is, it's like any other servers here. If one of the servers is compromised, their keys have to be removed. And in this case, if that server happens to be TGS for another realm, then that realm has to be removed until that is fixed. I mean, remove means they will get a new secret done, and then the life will start, but the previous tickets may not be useful. There is some disruption. All right, Kerberos version 5. So now let's look at the messages. We just finished the 11 things, but let's see. So the first message, which is not encrypted, has these things. It has options, IDC, realm C, IDG, times, and nonce 1. Alright, so the options might include that I want proxy and I want long term and whatever else you want. So there are many options that we'll talk about, but those are the things which we tell the AS that this is what I need my ticket to have. This is my ID, this is my realm, and this is the ticket granting server that I want, and so on. AS will send you, repeat whatever you have said, and then send you a new key for the ticket granting server. And obviously it is encrypted, whole thing is encrypted, so nobody else can read it, even though they can read the clear part here. This part is unclear. Well, let me correct myself. The ticket is in clear, but ticket itself is encrypted. So it's not really in clear. I mean, ticket itself is encrypted. These two are in clear. Ticket itself is basically encrypted with KAG. It says what flags the user requested, and the rest of the stuff should be obvious. Here's the key to use. Then the client takes that thing and sends it to the TGS. The important thing is, and it creates a new nonce and everything else, but the important thing is everything is clear here except for the ticket and authenticator. These two are encrypted. They go to the TGS. The TGS sends back the ticket for the server. All the keys are labeled by 2 letters or 1 letter. If it is labeled with 1 letter, then that is the secret you share with the AS. And if it is labeled with 2 letters, then it indicates the 2 principals that share that secret. So A is for authentication server and G is for TGS. So KAG is the secret that is shared permanently, actually in this case permanently. Not everything is permanent. For example, KCG is not permanent. KCG is generated every day. But KAG is permanent in some sense. So KAG is the key, that is, KCG is the secret between C and G. Now this is, we just got it as a part of our request, and so this is basically for today's use. Alright, so let's look at other keys. When I say KG, actually that was kind of, KAG was strange because KG is same thing as KAG. KG is the G's secret that it shares with the authentication server. And so this ticket, this line should go up here. So this is basically a detail of ticket G, which is in this line here. And so in this line, basically the server sends only the ticket for V, and the ticket V is explained here. So this client sends the ticket and the authenticator, and the authenticator ensures that basically, and this one can verify that basically I know the key. And then once it knows the key, it sends back the ticket and then something back which verifies that I know the key. Okay, so the question is, can we get Kerberos version 5? I think so. Well, here's the thing though, I will have to go and check it myself. I have not checked it. Kerberos version 4 is free download from MIT. That I know. Kerberos version 5, I would be really surprised if you cannot download it, because nowadays everything that is security is open source. So somebody would have made an open source version of Kerberos 5. Almost everything. Okay? So just look, just you have to say Kerberos version 5 open source. You will find it. Okay, so if you work for a company, you can do anything. If you work for BOSU, you could probably, play with BOSU's security system as much as you wanted to. Although if somebody else figured it out, then they will, ban you for life. So the thing is, there are 2 things. When you compile these sources, you could add instructions, and then really, you could put yours. But this being security, I'm sure that the organizations that do this, they have both the white team and the red team. White team are the guys who are working, and the red team are the guys who are testing them out. And so the red team would catch you, someplace. But not all companies are as smart, and so they might just have one person taking care of the whole thing, and in that case that person has complete control. We talked about options and flags. In the options, the client tells the server that this is the option flags I want, and those are the flags which are set in the ticket, right? So initial, so this is the ticket issued by AS. Alright, that flag will be set, and that will generally, in the previous description, it will be only set on the TGT ticket, ticket granting ticket, that is issued by AS. Pre-authent, the client was pre-authenticated by AS before a ticket was issued, so this will generally be set that the client has been authenticated, but it is quite possible that the client has not been authenticated. Alright, then there will be some additional authentication required. Hardware authentication. So how authentication was done? It was done using hardware like a smart card or something that the user purchased. So you know what is the quality of authentication. Renewable. The TGS can issue a new ticket that expires at a later date and therefore allows long lifetime. So previously it was limited to 21 hours, and even if you have some different units, so you could have a longer lifetime ticket. So these are renewable tickets. May post date. So this is another feature that you can issue a ticket which is in the future. And if it is a ticket in the future, then it is post-dated, and so it might be, let's say, in 2012. So then it will be also be, generally there is another flag somewhere, it is coming up here, yeah. So this ticket will be, this is what will the AS will say, that you can post-date it, and if it is post-dated, then TGS will set this flag. A ticket which is post-dated is generally invalid. That flag is set. So before it can really be used in 2012, you have to go back and validate it. So there is the state. See, now previously in version 4, there was no state. Now here is some state. So anyway, so this ticket is proxyable. This can be proxied with a different network address. So the network address is not fixed, and proxy, the ticket is, so proxyable is the one that is set by the authentication server. So authentication server tells TGS that, okay, you can issue a ticket which is proxyable, and then when it issues a ticket which is proxyable, then the TGS sets this which is proxy. Forwardable, that this can be forwarded, and then if it is forwarded, then it is forwarded ticket flag. So there are two flags: proxyable, proxy, forwardable, and may post-date and post-date. So those are like, okay. So the forwarded ticket is the one that can be forwarded by one server to the next. So A can get a ticket to Y.C via B, and so it can forward, can say to B that here's my ticket, and then can be forwarded to C. So rather than directly going, then the ticket goes like that. All the transient realms in the path are put into the ticket. That way you can check it out whether you want to accept that ticket or not. For example, if you get a ticket, let's say, just to name a country, suppose you get a ticket, and you get a ticket which came through some Russian validation. Now you are Defense Department in the United States, you may not want to trust it. So the whole path of where the ticket has been authenticated is put before you trust the chain. So anyway, so let's see if there are any more flags. No, that's it. So these are all the new flags, including an invalid one. So somebody may ask you why you have to issue an invalid ticket. Well, the reason is the ticket is invalid today, but it can be validated later on, post-dated ticket. Sometimes, I mean, now this is, I'm just guessing here, is that you want to have things that either continue for a long time, and it's not worth starting if they cannot continue for a long time. You may want to run a very long batch job, which is good for tomorrow. I will run till tomorrow. So ideally you don't want to start unless you get a ticket for 2 days. So you get a ticket for today, and then you get a ticket for tomorrow. And the tomorrow's ticket, you have to come back again. But the good thing is that you already got the ticket. You don't have to go to AS server again. So that's all it does, is it saves you that going back to AS server. You can get it validated again from TGS. I don't know whether that is a big deal, but you don't have to go to AS again. You can get all the tickets for the future for that job, and then you can keep going to TGS to validate them. So Kerberos does not use public keys. Kerberos uses only secret keys, right? And we have two versions, version 4 and version 5. And version 5 is the standard version now, basically standardized, generalized, and so on and so forth. And these are these generalizations, and these are how it makes use of KDCs in the ticket. Well, nowadays we can use certificates for authentication. So if you wanted to use certificate, then the certificates could be kept at KDC. So if you want to talk to A, wants to talk to B, then it could go to B and say, please give me the certificate for B, and you will get the public key for B. Now the reason you want to get from KDC is that now you are basically, you can trust that information. It is encrypted with the private PR. PR is the private key of the authenticator, KDC. Everybody knows the public key of the authenticator, right? So with that you can get the public key of B, PUB. Then you can send the message to B By the way, you also get the address and ID of B. So you can send the message to B, ID you already sent anyway. Send the message to B and you can say, here's my nonce, and the message is encrypted with your public key. So if it reaches the right place, it wants to make sure that it knows the public key of A. So it goes to KDC and says, can you give me the public key of A? A sent me this nonce, and A, and what is his public key? So the answer comes back, here is the ID and here is the public key of A, and here is your request. PUB, PR authorized, and A, this is the nonce you sent me, here is the session key, and here is the ID of A and B. So there are two things here. Here is the public key of A and here is the session key. Session key is specified here, right, along with the nonce. So then B responds back with, here is your nonce, here is my nonce, and here is the session key. Now prove me that you understand all this. So it says, yep, I understand, here is your nonce. All right, why are we using nonces? So that we can prove that this other side has the key. If the other side cannot tell us the nonce, means they don't have the key. A sends a nonce to B, which is actually in the clear. No, it's not in the clear. It is actually encrypted, so it wants to make sure that somebody who has the private key of B will only know NA. And this one is encrypted with two keys. And so somebody who has the private key of A and public key of authentication server will know this, and B. So here is your nonce back. And so KS is the session key that they can use from now on. So everybody knows the public key of KDC. Everybody knows the public key of KDC. So this, remember, this is asymmetric encryption. So anything that is encrypted with the private key is decrypted with the public key. Anything that is encrypted with the public key is decrypted with the private key. So everybody can decrypt this. Yeah, that's a good question. Maybe this is the question. Is that actually it doesn't have to be A, even C would know PR authentication, public key of authenticator, and will get IDB and PUB. All right, but that's no big deal, right? Anybody can decrypt that message and find out what is the public key of B. It's no use, basically. And let's see here also same thing. If anybody can decrypt this message, but it's no use. But nobody can decrypt this message. Now, what if you have to do one-way authentication, which is generally done in mail? When I want to send you a mail, I want to send you a mail where you can verify that it came from me, the signed email. All of you got from, for example, from Mart. That was one way, because he didn't know your certificate, he just sent you an email, which you could verify that it came from him because he signed it. And so this is how that works. Because the message is long, we don't use the public key for message encryption. We encrypt the message with a secret key, right? Any random secret key. I can select and I can just use that to encrypt. But I send that key to you along with the message. That key is encrypted using public and private keys. So for encryption, better to use secret key and then the secret key using public key. So A to B, here is my public, here is the secret key KS. Secret key KS, which is encrypted with public key of yours. Okay, so here I think this you could not do if you didn't know the public key of B. So if I didn't have your certificate, I cannot send you an encrypted email. Alright, so what I can do though is I can send you a signature. A can send to B a message which is in clear, and I can send you my certificate. I can along with this certificate, I can send you a hash of this message, hash of that message using my public key, which is signed with my private key. Anybody can check it out with my public key. If they have my certificate, they can check it out. So that's what we did, was basically if somebody changes the message, then when the receiver can say, well, the message has been changed, sorry, this signature is invalid. I don't know, George, were you able to resolve that ever, or your signature is always invalid? But you had to manipulate something. What was that you manipulated? Yeah, okay. All right, so some companies, I think, do play with these messages, and you cannot send signed messages because the message will be changed. They might add things like disclaimer that this message is only for public business use, blah, 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 and we don't take any responsibility, this and that. If they add anything to the message, your signature is no good. It's going by not in our chain of trust. Okay, so I think the problem in this case was different. The problem was that his certificate was signed by a CA that we didn't know. That was not in our systems. So we could not verify the certificate. So everybody understands that how I can send you a signed message only if I don't know your public key. That means if I don't get your certificate. But when I send you a signed message, what I'm doing is I'm sending you three things. I'm sending you the message in clear. I'm sending you a hash which is using my private key. So it is guaranteed that I sent it. Anybody can verify that with my public key. And I will send you a certificate along with it. Right? Now that certificate you can import in your Outlook. So you have my public key built in now, right? So that is why we needed to go to the second step, which is encryption. I need the public key. That I can do only once I get a certificate from you. However, note, someone else can replace the signature and encrypt the message and signature. Can replace the signature and encrypt the message and signature. A to B, here is a message with public key PRAHM. So the recipient must know the A's public key. Yeah, and therefore A certificate is sent with the message. Yeah. So that's correct. Basically, if I don't send you the certificate, then somebody can just manipulate both the signature and the messages with any private key. C could use its private key and say I am A, and here is the signed message. But that cannot be done if you have a certificate which is signed by somebody that we know. So actually that is what we did. We just accepted a certificate that was signed by somebody we don't know. All right, so that's trivial. We already did this exercise. Now we understand why we need the certificates first, and why we need to send a signed message first, and then we can do the encryption.